Okay, here's our example using Biot law. We are given a long wire. Okay, that has a current in it. And we want to find the magnetic field at this point P. Okay, find B at point P. All right, so let's solve. All right, so we're going to start with the Biot law. Field equals mu naught I over 4 pi integral ds cross r over r squared. Cross r hat. Okay, so what do we have here? We actually have this little differential right here. We have this dx that's in the I hat direction. We're going to draw a, this is going to be I hat, this is going to be j hat direction, or our origin is going to be right here. Okay, and from this point right here, we're going to have our field vector for this one is going to point right at B, like that. And this is in the r hat direction right there. And this angle right here is going to be, this angle will be theta 1. And we're going to have another one, so just work with me here. We would have another comparison over here that this is going to be our field from this end, from this. That's going to be theta 2 over there, so long as we are measuring from the outer edge, that we're consistent about which edge we're measuring the angle from. Okay, so we can start working our Biot law. Our ds, this is a straight line, our ds is really going to become dx I hat. Okay, so this is going to be dx I hat cross r hat over r squared. Well, I times r, I hat times r hat, those are unit vectors, right? And so anytime, if they're both unit vectors and they don't have any units, they're dimensionless. They're just a direction. They have nothing to them. All that's going to give us is sine theta. All right, so like if we have a cross b, then a cross b, the value of it is a b sine theta. But if these are units, then they just disappear, and we get our b to equal, and I cross r, by the way, is going to be, so if this is I and this is j up here, this is j hat, I cross r is going to give us up, which is going to be k hat. So, or b is going to equal mu naught I over 4 pi integral of dx sine theta over r squared in the k hat direction. All right, now this should make sense. So we've identified that our field that's actually acting on this is going to be in the k hat direction. Is going to be the field on that particle. Now, from here, we have to get everything in terms of theta. And so, how are we going to do that? Well, we need to get both of these, this dx and this r, into terms of theta. All right, now, if x, we're going to take this. This is going to be our x distance right here from, if that's our origin. So that's our x. All right. So x is equal to x equals. Oh, I'm sorry. I didn't divide this. This is the distance a away from the wire. So our value x in terms of r and a is going to be, well, we don't even need r, because as long as we have theta in there, theta 1, then x is going to equal negative a cotangent theta. Okay, and our r, so dx then is going to equal, you can look this up, okay, like I did. Okay, that dx is going to be a cosecant squared d theta. But we're not done. We also have to find what r is, and so r is going to be equal to, well, let's see, a over r. Sine equals a over r. So sine equals a over r. I want to get a by itself, so I'm going to switch. So it's going to be a over sine theta equals r. So now we plug these guys into our equation, and we get something kind of cool here. And it will be worth our going through that pain. dx is now a cosecant squared theta sine theta d theta. We have to bring that sine theta and d theta. All right. Still k hat. All over r squared, but r squared is a over sine theta. But 1 over sine is, well, 1 over sine is just cosecant. So this becomes a squared cosecant squared theta. That cosecant squared goes away with that one. This a cancels with one of those. Okay, and what are we left with but mu naught I over, well, a is a constant because that's just the distance from the wire to this point, so we can pull out an a, 4 pi a, and this just becomes sine theta d theta. Integral from theta 1 to theta 2, theta 1 to theta 2 of sine theta d theta. Now, what does this equal? Well, the integral of sine theta is negative cosine, so that gives us negative mu naught I over 4 pi a cosine theta 2 minus cosine theta 1 k hat, or we can multiply that, get that negative in there, and all of a sudden we have our magnetic field equal to mu naught I. All of a sudden, I say that mockingly. It's not really all of a sudden. It took us a while to get there. But mu over I, 4 pi a, cosine of theta 1 minus cosine theta 2. Remember, we multiplied the negative in there, which lets us to switch them. K hat, and this is our magnetic field from this particular case along a straight wire. But think about this one. What if the wire was infinite? What if it went on for a really long time, particularly in comparison to A? Okay, which is how we're really going to define this, that if A is really close to the wire, that's going to make what for theta 1? Theta 1 is going to be pretty close to 0, right? Well, cosine of 0, okay, is going to equal 1. And then if we go out here to theta 2, and theta 2 is way out here, theta 2 is going to be pretty close to 180 degrees. And so cosine which equals -1, this all of a sudden becomes 1 minus a -1, which becomes a 2, and this leads to if the wire is infinite, okay, then our B is going to equal mu naught I over 2 pi A. This becomes 2, cancels with the 4, and this equation you should memorize. Okay, because this is the magnetic field near an infinitely long wire with current I. This is the distance from it. In fact, if it's an infinitely long wire, then the distance doesn't really matter, does it? No. Okay, if it's infinitely long, then any distance from the wire is infinitely small. And so mu naught I over 2 pi A is something you guys should memorize for the magnetic field near a wire. Okay, now that's going to take us to our second example here, which is actually really short. So, example 2. Example 2. We have a point, we have a current, okay, and I is coming this direction. All right. Hopefully you guys can tell that if the current is directly at this, coming directly at this, that there would be no magnetic field. Okay, it should make sense for that right now, but we'll get into that here in a sec. Okay, here's a point. It is a distance r. Okay, so this distance is r, and it subtends an angle with a circle of theta. That right there is theta. Although I've been drawing theta with my purple. Ooh, that's really not a pretty... There's our purple theta. And I did not draw that very accurately, did I? So let me see if I can... I should have this out more often because my drawings are not... They don't look as cool as they should. This should be along that line right there at that point. And so this should be our current. I want that to be the current, not that one. In fact, I will make that disappear. Ta-da. You never knew it was there. All right. So remember, dB equals mu naught I over 4 pi integral of ds cross r over r squared. Okay, remember, this is Biot-Savart law, is the field law for magnetic fields. It is the analog to gm over r squared and kq over r squared. This is its version of that. Okay, well, we're going to integrate this. We're going to get integral of dB. Okay, is going to equal mu naught I over 4 pi, but because this is a curved wire with a constant radius, r squared is constant, and we can just pull that right out. Okay, and so we are left with integral of ds cross r hat. This should be a hat here, not a vector. ds cross r hat. R is just a direction, so it has no dimension, so it's not going to count into our integral. And so integral ds is just s. All right, so that's just S. All right, now our theta is equal to our S, which is now the arc length here of the circle. Okay, S is the arc length. All right, and so our theta equals S divided by R, if we're thinking in radians, or S equals R theta. So we can rewrite our B to equal mu naught I over 4 pi R squared times R theta. That R is going to cancel, that's going to cancel, and this becomes mu naught I for 4 pi R. And let's figure out our direction. Oh, I'm sorry, there's a theta here. Okay, and let's figure out our direction here, because we've got, that's our R hat, right? And our current our current is our ds, which is in, it's traveling along here. Okay, so ds cross R is going to be into the page, which would be negative k hat. Which would be in that direction. And that's how we do it around a curved wire, around our point in space. So this is what we use to determine the magnetic field at a point in space from a wire with current in it. Okay, we'll see you guys. That's a whole bunch of stuff you guys need to digest, and I'll see you guys on Friday so we can discuss it.